Hello again, Math 10Cs. In today's lesson, we are going to continue to look at dealing with systems of linear equations. But maybe just as a quick little review note before we do move on into this lesson, in terms of like what it means to actually have a system. When we define a system in physics, we define it as being a collection of two or more objects. Now, in mathematics, when we're looking at linear equations, we could define a system of linear equations as being composed of two or more equations. Or if we graph that, a system of linear equations would have two or more lines. Now, for most of high school math, we would only ever consider two lines at a time. As soon as you introduce a third line and try to examine three lines at a time and try to solve the system, it gets like really, really complicated. So that is not something we'd be looking at in high school math whatsoever. And the other thing is, in terms of solving the system of linear equations, we looked at this last time graphically, and the solution to a system of linear equations is the intersection point between the two different lines. Now, we're going to take this a little bit of a step further today because we're going to look at systems where we can actually have no solution or we can have an infinite number of solutions. There's actually three possibilities. We can have a system of linear equations that has zero solutions, exactly one solution, or an infinite number of solutions. Now, the book starts off by doing an exploration activity with a word problem. I don't find that's the most appropriate way to introduce this concept because I think word problems tend to be a bit more difficult. So we'll deal with the word problems more at the end of the unit. So let's just skip ahead to the next page. Okay, so it says, in all of the examples from our previous lesson, each system of equations had one unique solution. And again, the one unique solution would be the intersection point between the lines that we graphed. However, it is possible for a system of linear equations to have no solution, exactly one solution, or an infinite number of solutions. And in this first class example, we're going to show that. So we'll see what it means to have like these three different scenarios. Okay, so example one says graph each system on the grid below and then state the number of solutions for each system. Now, I'm going to use a graphing calculator to draw these. So let's start off with A. Okay, so what we're going to do is into the graphing calculator, I'm just going to plot these two equations into y1 and y2. So in y1, I'm going to plot x plus 5. And then in y2, I'm going to plot negative x plus 1. Okay, so let's go over to the graphing calculator. Let's clear this. Let's go to y equals. Let's get rid of the equations from yesterday. So hit clear, go down, hit clear, and then we're going to enter those equations into the calculator. So the first equation was x. So again, the x button is just to the right of the alpha symbol. So you have x plus 5, and we'll go down. And my next equation is negative. So the negative button is to the left of the enter one. So you have negative x plus 1. Okay, let's start off by just seeing how this graphs using the zoom standard button. Again, zoom standard goes from -10 to +10 on both the x and y axis. And let's see, can I see an intersection? Can I see the x and y intercepts for both lines and an intersection point? Yeah, you absolutely can. Okay, so let's go back now to the Smart Notebook and let's try to like just quickly sketch what this graph looks like. So, okay, so I'm going to pull some lines here. In fact, let's try to stay consistent with the line colors we actually see. So let's first of all grab a blue one. Okay, blue line. And again, what did that blue line look like? Okay, so I believe it was something like this here. Okay. We can just sketch it. We don't need to like be like completely accurate in how we sketched it at this point. Okay, and then we can just add those arrows to the end of it. So that's the first line. And then if we go back here, the second line, I'll make it red. Again, much easier for you to draw because you could use a ruler to do this. Okay, what did that one look like again? Go back here. Okay, it looks like something like this. And again, we're just sketching it. Okay, so let's add my arrows just so the graph keeps going beyond the grid. Okay, now, if you look at the graph, this would be like something we could have looked at yesterday. These two lines have a single intersection point. So my single intersection point would be located right here, okay? Now, if you have a single intersection point means you have exactly one solution, okay? So I can just write this down here. Let's just go here. So if you have one intersection, that means the system has exactly one unique solution. Okay, we're not going to use the intersect feature to determine that right now. The important thing is just to identify we have exactly one solution. Okay, now let's plot the second one in here. So in y1, we're now going to change y1 to 2x minus 8. And then we're going to change y2 to 2x plus 6. Okay, so let's go back to the graphing calculator. Y equals, let's clear these ones from part A. So my first equation is now going to be 2x minus 8. And my second equation is now going to be 2x plus 6. Okay, let's start off with the zoom standard. So zoom 6 and see what we get. Okay, now if you look at the graph here, we can actually confirm this by looking at the equations. I do not see an intersection point. And even if you actually zoomed out and looked at the graph like in an area beyond like -10 to +10 on the x and y axis, these two lines would never actually touch. Now, let's go back here and let's just sketch them, and we'll talk about like why they will never actually touch. There's something about the equations that would tell you that they would never touch to begin with. Okay, so let's go back and let's just sketch this. So let's grab a blue line. Okay, what does that blue line look like again? Okay, so it starts like right there. So it just looks something like this. Okay, and then let's sketch my red line. And my red one, okay, go back here, looks something like that. Again, we can add those arrows at the end just to show the graph keeps going. Arrow at the end. Now, it turns out these two lines will never actually touch each other. Now, the reason they don't touch each other is because, and you may have actually determined this already, but the reason these two lines do not touch each other is because they are parallel lines. If you look at the equation in the form like y equals mx plus b, both of these have the exact same slope. So if you have the same slope, it means the lines are parallel. And if the lines are parallel, they can never actually intersect. So if you have 0 intersection points, this means that the system does not have a solution. Okay, so there would be no solution to your system of linear equations because you must have an intersection point to obtain that. Okay, so let's look at the third one now. So we have y is equal to 3x minus 2. So we're going to plot that equation into y1. Okay, so we'd have y1 is equal to 3x minus 2. Now, the other equation we've got to do a little bit of work for because right now it's not in a format that we can actually plot it in the graphing calculator. We have to get y by itself. So the way I'm going to do that is I want the y term to be positive. So I'll start off just by adding 2y to both sides of the equation. So we'll add 2y, add 2y. And then this would look like 6x minus 4 is equal to 2y. To get the y by itself, divide by 2, divide by 2. Okay, the y's would cancel off. Now I'm going to move the y over to the left-hand side. So you then have y would be equal to, take each term in the numerator, divide by the denominator. So this would be 6x over 2 minus 4 over 2. And then this would give me y is equal to 6 divided by 2 is 3. So you'd have 3x. And then 4 divided by 2 is 2. So you'd have y is 3x minus 2. Therefore, we're going to plot into y2 3x minus 2. Okay, wait a second. This equation, y equals 3x minus 2, and this equation, 3x minus 2, they're the exact same equation. Okay, so let's go to the graphing calculator and plot this. So let's clear our previous equations. So let's go y equals 3x minus 2, and then let's just simply graph it. Okay, so that's a line that goes up and towards the right. Now, if we plot a second line, that second line is just going to go directly on top of that first one. So if we go back here, 3x minus 2, graph it. Yeah, it actually just overlaps the other line. So if we go back to here, oops, let's go back to the Smart Notebook file. Okay, and let's plot my line. So let's grab blue line. Okay, what did it look like again? All right, so it looks something like this here. Okay, so that's y1. And then if you plotted y2, it would just directly overlap. Okay, so I'll try to draw it so it's just kind of like, just so I can see the two different colors. Okay, so there's a bit of overlap here. And again, we can just draw the endpoints, or not the endpoints, just draw the lines at the end. So arrow, arrow, and then arrow, arrow. Now, I drew them a little bit offset, but they do completely overlap. Now, the question here would be, like, how many intersection points are there? Well, if you have one line directly on top of the other line, there are actually an infinite number of intersection points, because there'll be an intersection point at the bottom, there'll be an intersection point in the middle, intersection point at the top. In fact, as you go along the line here, because they perfectly overlap, like, they would intersect at every single possible point. So in this situation, what we would say is we would have infinite intersection points which means the system itself actually has an infinite number of solutions. Okay, so if you have one intersection point, we have one solution. If my lines are parallel, you cannot possibly have an intersection point, therefore we have no solution. And if we have two lines that are actually the exact same line, they would perfectly overlap, and therefore we would have an infinite number of solutions. Now let's summarize this information in this table. Okay, so it says, here's a graphical example of lines that intersect at one point. Okay, so I'll just sketch this. I'm not going to pull a ruler out here. I really should, but I just want to save a little bit of time. Okay, so this might be an example of like where you have one line that kind of just goes up and towards the right, and you have another line that goes maybe down and towards the right. Okay, now just fill in the rest of the table here. Okay, so for this example, if we have lines intersect at one point, how many solutions are there? There is one solution, okay, because you have one intersection point. Now it says, what can you tell me about the slopes and intercepts of two different lines that only have a single intersection point? Well, as long as the slopes are different, the lines will at some point intersect. So again, these slopes are clearly different. Like the red line is a positive slope, the blue line is a negative slope. But as long as their slopes are even slightly different, at some point these lines will intersect. Okay, so what I'll say here is these slopes are different. Okay, so that's going to be a way we know that if we only have one intersection point. If we have two lines and they have different slopes, they will have one intersection point, and we could actually know that without even graphing. Okay, the second one says, how about if we have lines that are parallel? Okay, so let's do a red line like this. Do my best to draw like another blue line as parallel as I can get. Okay, not bad. Okay, so what do we know about this now? Okay, so if we have lines that are parallel, they must have slopes that are equal. And we already know that. We know that parallel lines have the exact same slope. And if they're parallel lines that have the same slope, then their the x and y intercepts are going to be different as well. And I can see it's here. The two x intercepts and the two y intercepts are a little bit different. In this case, how many solutions do you have? 0, because those two lines never actually touch each other. Now it says, graphical example where you have lines that are coincident. Coincident means that they just overlap one another. So we could have like a red line that does this, and we could have a blue line that just goes directly over top of it. And then okay, how many solutions do we have if they're overlapping? Well, the lines touch at every possible point. So you'd actually have like an infinite number of solutions. Now, how do their slopes and intercepts compare? Well, these lines they're the exact same line. If it's the exact same line, they have to have equal slopes. And the same intercepts. Okay, so example 2 is we're given a bunch of equations, and what we want to do is we want to determine how many solutions there are, 0, 1, or infinite, but we're going to do it without graphing. Okay, so we need to figure, we don't want to actually plot this in the graphing calculator. We're just going to use the information about the actual equations to do this. Okay, so the first one, we have two equations. We have 3x plus 5y equals 15. Now, the best way to compare linear equations is in y equals mx plus b format, because you can identify the slope and you can also identify what the y-intercept is. So the first thing I'm going to do is I'm going to get 5y by itself. So I'm going to subtract 3x, and I'm going to subtract 3x, and then I would have 5y would be equal to negative 3x plus 15, and then get y by itself, so divide by 5, divide by 5, and then this would give me the 5's cancel. Y would then be equal to negative 3 over 5x plus 15 over 5. 15 divided by 5 would be 3, so it would just be negative 3 over 5x plus 3. Okay, now let's compare the two equations. Okay, so here's the first equation, and here's the second equation. Now, what I notice about these two equations right away is these two equations, they both have the exact same slope. Okay, so let's just write down here. Okay, so I'll say since both have the same slope, okay, and we know the slope here, m, is equal to negative 3 over 5. Since they both have the same slope, but they have a different y-intercept. This guy would actually have no y-intercept, because this would be y equals mx plus b. It would just be like adding 0. Okay, so since they have the same slope, but a different y-intercept, we have parallel lines. And if we have parallel lines, we have no intersection point, and therefore we would have no solution. And again, if you want to confirm that, you could plot both those lines on the graphing calculator, and you would just see that the lines are parallel. And if they're parallel, they never touch. If they never touch, no intersection point. No intersection point, you have no solution. Okay, next one. We have x minus 4y plus 8 and y equals 1/4 x plus 2. Okay, so the second equation is in y equals mx plus b format, but the first one is not. So let's first of all try to get that into y equals mx plus b format. Now we don't want to have a negative sign in front of the y term, so we'll bring y over to the other side. So we'll add 4y, and then what I would have is x plus 8 is equal to 4y. Okay, let's get let's get the y by itself. So divide by 4. Okay, bring the y to the other side. So this would be y is equal to x divided by 4 would just be 1/4 x, plus 8 divided by 4 would just be 2. And now let's look at what we have. One equation is y equals 1/4x plus 2. The second equation is the same one. It's y equals 1/4x plus 2. So what happens if you have the same equation? If you have the same equation and you plotted them, the two lines just completely overlap. So what we can say is, since both lines are the same, then which means that they overlap. Since both lines are the same, they overlap. And if they, is that a P there? Doesn't look like a Q. Okay. Okay. Since they both overlap, that means you actually have an infinite number of solutions. Okay, and then finally, we have C. So we have both these equations are not in y equals mx plus b format. So let's start off by getting them there. Okay, this one at least has y already, y with the coefficient of 1. So we're going to subtract 7x. Subtract 7x. And then we'd have y would be equal to negative 7x plus 12. Okay, that's the first equation. The second equation, we want to get y by itself, so we need to get the y term positive. So I'm going to add 6y to both sides of the equation. Add 6y, add 6y. And then also let's get rid of, actually let's do this one step at a time. Okay, so this would then be x is equal to 6y plus 5. Get rid of that 5 to isolate the y. So we're going to subtract 5 from both sides. Then we'd have x minus 5 is equal to 6y. Then get the y by itself, so divide both sides of the equation by 6. Divide by 6. 6's cancel. And then you'd have y would be equal to, x divided by 6 would be 1 over 6x. And then negative 5 over 6 is a fraction that does not reduce, so it just turns into negative 5 over 6x. Okay, so here's my two lines. So I have y equals negative 7x plus 12. And then I have y is 16x minus 5x. Now, as we identified in this chart up here, the instant that you have different slopes, okay, it means at some point, okay, who knows when it'll happen, but if as long as they have different slopes, at some point those lines are going to intersect, and they will intersect just a single time. Okay, so I'll say since the slopes are different, this means you would have one intersection point, and if you have one intersection point, it means you have exactly one solution. Okay, and we determined all three of these, A, B, and C, without doing any graphing. But again, you could graph just to confirm it. Okay, so it mentions here that like sometimes when we like graphically try to solve a system, we can't actually see the intersection point, in which case we're gonna have to adjust the window settings. Okay, so now let's look at a word problem. Now that we've actually looked at like kind of like the theory in terms of when you have like 0, 1, or infinite number of solutions. Okay, so it says at a local high school, the students' council decides to sell sweaters. Decide to sell sweaters to students. The cost of designing sweaters included a fixed cost of $600 plus $5 per sweater. Okay, the student council plans to sell the sweaters for $25 each. The cost and revenue can be represented by the following system of equations where D is the dollar cost and N is the number of sweaters sold. Okay, so we have two equations here. So my first equation says the cost of sweaters sold in dollars is 600 plus 5N. So what this equation is doing here is it's modeling, so let's box this equation. It's modeling this statement. So it's saying how much does it cost to actually like make these sweaters? It'd be $600 plus $5 per sweater. So, and per sweater is, we're using the variable N to represent the number of sweaters. So the dollar cost of producing the sweaters would be 600 plus 5 times the number of sweaters we actually sell. Okay, so that's the first equation. And then it says, how much money do they make? Well, it says they make $25 for every single sweater sold. So my revenue would just be $25 times the number of sweaters sold. So that's going to be my second equation here. Okay, now it says use a graphing calculator to graph each equation and sketch each graph on the grid below. Now, the first thing I'm going to do is I'm going to change the variables because, again, we plug things into the graphing calculator. We use y and x instead of like d and n. So I'll say let. Now, we're going to let y equal d because y is already isolated. D is isolated, and we want y to be isolated to plug it into the calculator. So I'll say let n equal x and d equal y. So my first equation, the cost equation, would then turn into y is equal to 600 plus 5 times x, which is basically going to be a line that has a y-intercept. We can rewrite it in y equals mx plus b format if you want. So this would be y equals 5x plus 600. Okay, so that's going to be a line that has a slope of 5 and it has a y-intercept of 600. And if we want to, we can just write it down in terms of how we plugged it into the graphing calculator. So we're going to plug in y1 is equal to 5x plus 600. Okay, so that's going to be the first equation. Now the second one, so we're going to turn d into y and n into x. So then the second equation would then become y is equal to 25x. Okay, turn that into the format we're going to plug in. So this would then be y2 is just 25 multiplied by x. Okay, let's just box this. And we're going to plug these into the graphing calculator. Now, when we do this, it's not going to give us an intersection point we can see. So we're going to have to tweak the graphing calculator to deal with this. Okay, so let's go back to y equals. Let's clear these two equations. And then the first equation would now be 5x plus 600. So that's my cost equation, which is that's how much it costs to make these sweaters. 5x plus 600. Because again, it's a $600 cost plus $5 per sweater made. And then the second equation is the revenue equation, which is we make $25 per sweater sold. So it'd be y2 is 25 times x. Okay, let's plot this and see what happens. Okay, so if I graph this, I see the red line. That's about it. I don't see the blue line though, so that's a big problem. Okay, so let's maybe like try to use you can play around with this. Like you can adjust the window settings manually if you want, or we can try to use like the zoom out feature and see if we can get this thing. Or how about zoom fit? Zoom fit's usually like a good start. So zoom fit I think is zoom 0. Let's see how that does. No, that's not good because that one does not show the two lines intersecting. So how about we go back to zoom standard, which we still can't see anything, and let's try zoom out. So we'll hit zoom because it's too close in. Like we can't see the intersection point. We need to like zoom outward to potentially be able to see it. So we'll hit zoom 3, and it prompts you just to hit enter, and it's going to zoom out from the origin here. So if we hit enter, still don't see anything. Okay, let's hit enter again to go to even further. Okay, again, now I can at least see the blue line, but it's not quite good enough here. Okay, so let's hit enter again. Okay, I'm getting close to being able to see the intersection point, but not quite. And let's do it one more time. Okay, now I can see the intersection point. Now, this would be a really, really awful graph to like to plot on the actual grid. And actually, if we look at the example problem, it actually shows us how to it shows us how to create our grid. Okay, so if we go back here, it shows us we're going to make the y-axis go up to 1,000 and the x-axis go up to 50. So I guess we didn't really actually need to even tweak this, but I kind of just wanted to show you like what you need to do. I mean, like what I would do now without even looking at this is you can't have negative number of sweaters and you can't have a negative number of dollars here. So we can just start off at, we can just adjust those window settings. So let's go to window. So let's make the x-min 0. So x-min of 0 means you're starting off with 0 sweaters sold. And then we can go to y-min of 0, which means the cost is 0 or the revenue is 0. Okay, let's graph it now and see what happens. Again, like I can see the intersection point here, but there's just so much wasted space on the graph. So now let's actually just adjust the window settings to match like the problem we see. Okay, so the problem goes up to a maximum y value of 1,000 and a maximum x value of 50. So let's go to window settings. So we're going to change the maximum x value to 50, and we're going to change the maximum y value to 1,000. 1,000, not 10,000. Okay, let's graph this. Okay, that's a lot better. So now let's attempt to actually like sketch this on the graph, and we can identify what our window settings are. It doesn't hurt to actually be able to see the y and x intercept, and maybe I'll just add a little bit more wiggle room on the left side and the bottom side of the graph so we can see just a little bit more of this. So maybe we'll make the x min like -5 or something, and then we'll make the y min maybe like -100. Okay, and then see what it looks like. Okay, that matches more with like what the picture looks like. Okay, so if we go back here, the window settings, if I just want to write them out, would be, let's go back to my blue pen. Okay, so the window settings would be x. I think I went from like -5 to 50, going up by increments of 1. And the y, we went from, I think, -100 to 1,000. Again, going up by increments of 1. Okay, so let's sketch this now. So let's do the blue line first. Okay, so the blue line is going to be the first graph. So let's grab a blue line. Okay, now the blue line does start at like 600, and it has a slope of 5. So again, we only need to sketch this thing. So let's see like what it does here. Okay, so it starts at 600, goes up a little bit. Okay, so maybe like something like, no, I want you to do a blue line, not a black one. Let's get rid of that one. Just want to match the color of what I see in the problem. Okay, so we start at 600, and it does something like this here. I think that's reasonable. Yep, not bad. Okay, and then the red line starts at 0, and it's going to intersect somewhere around the top point up here. Now again, I'm just sketching this. We'll use the graphing calculator to figure out the intersection point in a moment. Okay, so let's grab a line. Let's make this one red. Change the thickness. Okay, where does it approximately intersect? Looks about like kind of like 3/5 of the way along the x-axis. So let's go back here. 3/5 of the way along the x-axis, maybe like something along right, pretty close to right there, maybe I'd say. Yeah, that's not bad. Okay, and I guess if you wanted to, you could draw the line, the arrows here. So I'm not going to draw it on this side because the graph does actually stop at like that axis there. So, but it could potentially keep going over to this side. Okay, now it says how much profit or loss is made if 20 sweaters are sold. Okay, so what we can do is we can use these two equations to figure out the number of the cost or the profit that's actually been made here. Okay, so the first equation is the cost equation. The second equation is the revenue equation. The profit would just be the revenue subtract the cost. Okay, so let's calculate this. Okay, so my cost would be D is equal to 600 plus 5 times N. Okay, if 20 sweaters are sold, we're going to plug in a value of N equals 20. So that's going to be D is equal to 600 plus 5 times 20. Okay, so my cost of making 20 sweaters would then be $700. Now the revenue, we use the second equation for. So that equation is D is equal to 25N. So this would then be, replace N with 20, so 25 times 20. Therefore, my revenue would then be 25 times 20 would be $500. Now, to figure out the profit or loss, well, your profit would just be equal to the revenue minus the cost. So this would be equal to, the revenue was 500. Subtract the cost, which is 700. And then you would have a profit that would actually be negative $200. So that's actually a loss. So if they only sold 20 sweaters, they're not making, I mean, they're actually losing money in this situation. Okay, what if they sold 50? So it's quite a bit more sweaters. So we can do the same thing here. So the cost. So your cost equation is D is equal to 600 plus 5 times N. So you have 600 plus 5 times, now we're selling 50 sweaters here. Therefore, D would then be equal to 850. And then your revenue you would have D is equal to, was it 25 times N? So that'd be 25 multiplied by 50. And then this would be 1250. Okay, then your profit would just be the cost of the revenue minus the cost. So that would be equal to 1250 minus 850. So in this case, we're actually making money. So you'd make $400. So it would be a profit, not a loss in this situation. Okay, C. It says the break-even point is the point where no profit or loss is made. Mark this break-even point on the grid. Okay, so here's what's going on. So here's my intersection point. Okay, so this is kind of like this is the break-even point. Okay, so we break even. So that's the spot where my profit or my cost and my revenue would be equal to each other. So what this actually means is, now we'll determine how many sweaters you need to sell to do that in a second, but it basically means if like you sell a number of sweaters that would fall below the break-even point, okay, like this, it means that you would have a loss. If you sell a number of sweaters that would be above the break-even point, then you're going to make profit on your sales. And if you break even, it just means there's no profit, but there's no loss as well. Okay, now, D says use the graphing calculator to determine the number of sweaters that must be sold in order to break even. Okay, so we're going to use the calculator to figure out what that break even point is. I mean, I could estimate it off the graph here, but I sketched these lines, so this point is probably not completely accurate. Okay, so let's use the graphing calculator to do this. Now, we already have my lines plotted in here, so the function I'm going to use to figure out the intersection point is I'm going to hit second, and then trace, which will access calculations, and then hit number 5 for intersect. Take the cursor and get it as close to the intersection point as you can. Okay, so I'll bring this one over here, hit enter, and then on the second line, again, get that cursor as close to the intersection point as you can, hit enter, guess the solution, and what it tells me is that the intersection point is x is 30, y is 750. So let's go back here and write that now. So, okay, so x is 30, and then y is 750. But let's write down the correct variables. The correct variables are n is x and d is y. So which basically means that, let's write down n first here. Okay, so instead of x, we have n. Therefore, to break even, we would have to sell 30 sweaters. And if you're wondering, just if you sold 30 sweaters, the y value, D, would be 750. Okay, so we get the number of we get the number of sweaters. You need 30 sweaters sold to break even. Because at that point, what the 750 number means is the 750 number would mean that your cost is $750 and your revenue is $750. Those two numbers would just offset each other at that point. Okay, now it says, if all 850 students in the schools purchase a sweater, how much profit would they make? Okay, well, we can do the same thing as like we did in part B. We just calculate the cost, calculate the revenue, and then just subtract the two different things. Okay, so let's go back to my pen here. Okay, so cost. So if everyone buys a sweater, we're going to sell n equals 850 of these sweaters. So my cost equation is D is equal to 600 plus 5 times n, which would be 600 plus 5 times 850. Therefore, your cost D would be 4,850. Now, the second equation, which is the revenue, how much money we make from these sales, because we're like way above like our break-even point of like 30 sweaters, we're going to like make a ton of money here. Okay, so D would be equal to 25 times N. Replace N, the number of sweaters, with 850 because every person in the school is buying one. And then this would give me D would be equal to $21,250. And then to figure out the profit, you just go your revenue minus your cost. So it'd be 21250 subtract 4850, and then the profit would be 16,400. So again, go back up to the graph here. Like 850 would be well in this profit zone. In fact, it'd be like completely off the graph because the graph only goes up to like 50 sweaters sold. Okay, that's it for this lesson. And the questions that you can complete are do numbers 1 through 5, 8 and 9. Now, 8 and 9 are 8's a multiple choice question, 9 is a numerical response question. So just once again, the expectation is even though they're multiple choice numerical response, like when completing this work here, I want you to show the work. I mean, show work for all of them, including numbers 1 through 5 when you need to. Although I think number 1 is just you have to just simply identify if like you have one solution or like what it means to have like 0 solutions, 1 solution, or infinite solutions. Okay, so that's it for this lesson. We've kind of dealt with all the graphical parts of looking at systems of equations. And in the next like few lessons, we're actually going to start to solve these things algebraically. And I'll talk to you then.